Well, hello. Pudding and I are back for part two of our series today on how do we describe motion and how do we represent things motion in physics, because some of the regular techniques and things that we really get that we use. So in the last particular video, we set up the first idea about how we're going to describe something that's moving in a way that's not taking stop action photographs or trying to do something like that. How do we distill that down? And we use the concept of motion diagrams and specifically particle models, the little dot versions of motion diagrams, super simplified ones, to represent something moving basically in one-dimensional or two-dimensional movement. So what we're going to take a look at today is this particular video is to look at this concept of vectors. Now, I mentioned that, I brought that up in that last video a little bit about how we describe something's motion. And when we're talking about how something is moving, one of the things that makes physics very different than math is that, when you graph something in math, there's like this perfect XY, right, that we use all the time. I mean, graphs are graphs, right? That's what they look like the same thing. I'm going to move my cat. They look the same thing every time we do it, right? Whenever we draw, hold on, let me get this out of the way, my pen. Whenever we draw a graph, right, they always look exactly the same. We always do like this. This is our X. This is our Y. We always kind of go this direction. This is positive. We always go this direction. This is negative. Same thing here. This up really is positive. And then this way down here is negative, right? We always draw graphs like that in math class. We have kind of gotten into this habit of saying that that's the way that we're going to put graphs on paper. Well, the thing is that in physics, we've got to be a little bit careful about how we draw things and how we represent things. In fact, I shouldn't say we don't have to be careful about it. It's kind of a different kind of careful. We can kind of throw that concept out the window a little bit. We're still going to use coordinate systems. We're still going to talk about something moving, this direction and this direction. How do I talk about something's moving towards me at 2 meters per second versus something that's moving away from me at 2 meters per second versus something that's moving to the side, right? We have to have ways of talking about that. And we will definitely use graphs and coordinate systems. But one of the big things that makes it very different is that we need to realize as physicists that there is no XY axis in the sky. There's no perfect coordinate where 0, 0 has to be. As physicists, we get to decide which direction things are moving, or I shouldn't say that, how we're going to graph what direction things are moving. Because we can say, well, is walking towards the camera the positive direction or the negative direction? We always say, well, this way, the x-axis, right, going this direction, we always say that's positive. Well, what if something's moving that way? Sometimes it's just easier to say, well, that direction's positive. It's like when we orient a map. A lot of times when we orient an old-fashioned paper map, we always hold it so that north is up. But y'all know that when you're driving, north isn't really up. North could be this way, or this way, or this way. But north is very rarely actually this way, right? So when we're talking about coordinate systems and we're putting a map down, a graph of something's motion, we have a lot more flexibility in physics about how we arrange which way the positive direction is and which way the negative direction is. So for example, we've got this little motion diagram of this little runner here on the page, right? And it says, 5, 10, 15, whatever, 30 meters. We can also kind of assume that maybe they're going, every one of these photographs was taken at a second. So here's second number 1, here's second number 2, second number 3, 4, 5, 6, and 7, right? And we can say, all right, this is my 0 spot. And just like we've done in the past, like you've gotten used to doing, we could say that that direction to the right on the screen is the positive direction. Why not? We can certainly say that. There's no big deal in saying that at all. But we could also say that that's actually the negative direction. Maybe this guy's running back home. Maybe he'd already gone 30 meters that way, right? And now he's running back 30 meters the other direction. It's kind of a matter of our conversation. And so this part about when we're using vectors, we're going to be using arrows like this to represent not only how far did something go, but what direction it went. Because going 5 meters this way is different than going 5 meters this way, right? Because we could have just as easily said that this is a person running backwards. What if this is time equals 0 here? And this is time equals 1, and this is time equals 2, this is time equals 3. What if in reality the dude's moving this way, 5 meters the other direction? You can't tell really from this particular thing. I know we make those assumptions when we look at it that the person's moving that direction, but it could be the other way around. So part of this discussion in this particular video is just to kind of get you to let go a little bit of saying that to the right is always positive and to the left is always negative, or up is always positive and down is always negative, because sometimes it changes. Like if I'm dropping something, maybe if I have something falling to the earth, maybe I want that direction to be positive because it makes my math easier. If I'm throwing something in the air, maybe I want that direction to be positive. It just depends, because a graph is simply a tool for us to use to interpret something's motion. Same thing with where the 0, 0 point is. I can decide it's the starting point or it's 5 meters away from the starting point. I can make the call where the 0, 0 line is. I just have to define it. So that's one of the things that we talk about a lot when we're talking about where things are moving, is defining our directions. Which way is something going? So I've got pictures of not really, but pictures of the cat here. So let's say we've got the cat moves 10 meters, then moves 5 meters. Where did it end up? Well, that depends on a lot of things. And this is where the thing about vectors comes into play. So you guys know that this thing, 10 meters, is something like distance, right? How far did it go? But there's a different discussion that we talk about in physics a lot that's not just distance, but it's the distance in a given direction. This is what makes it a vector, because something is a little bit different. If it moved 10 meters and then moved 5 meters, well, where did it go? Well, it depends. If it moved 10 meters, I'll make my arrow kind of longer, 10 meters, and it also moved 5 meters, that's one place that it could end up, right? 15 meters away. But it could have just as easily gone 10 meters, right? And then 5 meters. And then it would have ended up literally in a different spot. 5 meters, 10 meters. Third possibility, could have gone 10 meters, and then it could have gone 5 meters. Very different direction. Now, the distances are exactly the same in every one of these. It's gone 10 meters, and then it's gone 5 minutes, 5 meters. What's different is the direction. Okay. The concept of having direction here is the idea of what a vector is. It's not just how far did you move, but in what direction. That makes a difference. And again, if you went 10 meters here and 5 meters here, you can tell these are a little different. Or we could go this way, 10 meters this direction and 5 meters this direction. Now, that's a whole different kind of thing. We haven't even gotten that direction. Going angles? What? We don't have to do angles, right? But it could be going at a different spot like this. So when we're talking about looking at talking about something's position and where it's moving, we need to know kind of the direction that things are moving. And we do this for right now with positive and negative signs. So for example, I could say the cat moved plus 10 meters and then moved minus 5 meters. As soon as I say that one of them's negative, I simply mean it's going in the opposite direction. So if I said it went plus 10 meters and minus 5 meters, that would be like this situation right here. Plus 10 meters to the left and minus 5 meters to the right. Opposite directions. Notice how I said plus was to the left. That's a little backwards than we would normally do in a graph. It doesn't really matter. It's just I'm calling that way plus and that way minus. Whatever works. I wouldn't use a plus and a minus in a situation like this. Here, I would actually have to give a more of a direction. I would have to say it turned 90 degrees to the right or something along those lines. You can't just say that this is positive and this is negative, because those are two different planes. So for what we're doing right now, we're just going to be talking about things in one dimension. So this could be plus 10 and plus 5. I could have easily called this one plus 10 and plus 5 as well. But if I called this one positive, then I'd have to call this one negative, right? We have to kind of define which direction they're going. So this is the idea of displacement. Displacement is about changing something's position in a given direction. So when we're describing these things, again, I've been talking about what vectors are, and vectors are basically arrows. That's really what it is. It's not just a distance, but it's a distance with a direction. So vectors, when we describe them, and we use vectors a lot in physics, when we're describing something's motion, we describe two characteristics of it. Number one is its magnitude. In other words, how big is that vector? A lot of times this is distance, right? It could also be some other things like speed, could be like time, could be a variety of different things. So magnitude, how big a vector is it? Is it 10 meters or is it 5 meters? The second thing that we always have in here is something about direction. And when we draw vectors, we always draw them as an arrow. We call them, there's a tip and a tail. And a lot of times this is called the tip right here, the tip or the head of it, right? So this would be like the start, and this would be the direction that it's going. I know the arrow, the way that my pointing on the video is opposite from what happens on the screen. It's awkward. So again, it would be starting here and ending here. So again, you've got a certain distance, but now you have the direction that it's going as well. And this is the difference between, like I said, distance and displacement. Distance is it's 10 meters, right? Both of these vectors have the same distance, but they have different displacements. It's like if I tell you right now, go walk 10 meters out your front door. Well, what direction, right? It depends. So the direction is the displacement part of it. So that's the concept of vectors, right? They not only have a size, they also, which is magnitude, they also have a critical direction. And a lot of times in our directions, like I said, we'll add them, we'll use positive and negative signs to represent that. So when we're adding vectors, when we're trying to talk about how these things go together, this is my last slide today. When we're adding them, we're talking about it went 10 meters and then it went 5 meters. We always add vectors in a phrase that we use here a lot. It is called tip to tail. Okay, so here's what this means. If the cat moved 10 meters, right, and then it also moved 5 meters, same direction. In this case, notice how I lined these up. They are tip to tail. The tip of the first one is at the tail of the second one. They're lined up start to finish. So we could say then our final distance, if we want to figure out what that is, let me move this out of the way. I'm going to change my color here. Our final displacement that this cat went was a total of, like this, 15, right? It's easy. We just add them together. Literally, the adding of vectors isn't that hard with what we're going to do right now, as long as we have them lined up tip to tail. That gives us an idea of the magnitude and direction of the resultant vector. That's what this is called, SULTANT. The resultant vector is what you get when you add two other vectors together. It's the sum of them, basically, is what the fancy word that we use for it. So let's take a look at one of these other options here now. What if the cat went 10 meters this way and then went 5 meters this way? So now if we're going like this, plus 10 and minus 5, I know the math on this is really easy. This is not about the math. This is about how do we represent this in terms of a diagram that makes sense. Okay, if our cat went plus 10 and then minus 5, notice if we're trying to figure out what our resultant is here, these two vectors are not placed tip to tail. These two vectors are placed tip to tip. So what we would do instead is we would draw them in this fashion. Let me erase this one real quick here. We would draw them instead more like this. It went plus 10 meters, and then it turned around and came back 5 meters, and this would be negative 5, like that. I'm putting my negative sign in there because it's going the other direction. Okay, so that's how that would work. Now, what is our resultant vector? Okay, drawing the resultant vector now is a little bit more tricky. So the resultant vector is always drawn from the very first starting point to the very last ending point. Tip, I guess it's tail to tip in that sense. The very first tail to, or the very last tip, something along those lines. So you do the same thing here, but take a look at how it is now. Now it's like this, all right? So it starts there and it ends here, right? It didn't go over, take a step over and come back. It literally went forward 10 and then came back 5. So what is the resultant for this? Well, the resultant goes from here to here. It's 5 meters. I know you know that, the math-wise, but what direction is it? Okay, the net gain of this cat, if it went to the right 10 meters and to the left 5 meters, then the net gain here is this direction, plus 5. That's a resultant. I know this is kind of weird. I'll do a couple more of these. So again, it went to the right 10 and to the left 5. The net gain is, the net movement is to the right 5 spots, or forward and backwards if you want to talk about it that way. But again, you always go from the very first tail to the very last tip. If you add them tip to tail, that's what you're ending up adding them up. So let's take a look at another example of how this could be laid out. Another possibility could be, well, I don't know, if they're either going the same direction or they're going opposite directions, right? Oh, I can do an angle one. Okay, so if they're going forward 10, like that. Let's say they went this way 5. That. So now where's a resultant? Okay, this is a little bit easier to see where the resultant is. Actually, students have an easier time with this one. Well, it's one single vector that goes from the start to the finish. One single vector that goes in a straight line from the start to the finish. So in this case, our resultant vector would be like this, the hypotenuse, basically, at an angle. we would just call that our resultant. So again, it goes from the very first start to the very last finish, and it always points the same way. So take a look. The tail of this vector or resultant vector is at the tail of the first vector. These are tail to tail here, and it's going to be tip to tip at the end by the time you're done. That resultant vector is the one straight line that you get to go on. You can do this, by the way, with a bunch of different vectors as well. So if we're trying to do some crazy cat race or something along those lines, to try to get them going, I go 10 meters this way, and then I go 5 meters this way, and then I go 10 meters this direction. I go up a bunch, and then I go back a bunch this way, something along those lines. Okay, what if the cat's going like that? Where's our resultant vector? Okay, our resultant vector literally goes from start to finish. Here's where we started. Here is where we finished. So literally, our resultant vector is like that. Okay. Again, we'd have to do a bunch of math to figure out exactly how long that was, and that's not where we're trying to get to. The whole idea is that when we're adding them, if it's going plus 10 and going minus 5, they're kind of on top of each other. But when we draw our resultant vector, it starts at that spot and ends at that spot. So our resultant vector, literally in the positive direction, whatever that unit was, 5 units or something like that. So again, adding vectors is a little bit weird. We'll have to do some of these examples as we get into later videos, especially in the second, third chapter when we start doing more of these at angles and stuff like that. Just to get you the idea about the direction, positive and negative is kind of up to us. We can decide which way is positive. And whenever we add vectors together, we always make sure that we don't lay them like with the tails next to each other. We always lay them tip to tail so that we can put them together. Okay, there you go. And I'll see you guys in the next one.